So now I hope that my screen is visible to you. I am using OneNote now. Okay, right? It is visible to you, right?
Yes, sir.
Yeah. So we are having a transformer. In the transformer, we are seeing about primary winding, and in that primary winding, if you are giving some current, and if there is some voltage source, and if you are giving some current, then the EMF induced is given by, okay, you consider it as E1, EA, EAB, that is the voltage drop which we have seen from this side because the current is entering the positive polarity, right? This is what we were seeing. So we told that E is equal to N into d phi by dt. Okay, so this is the flux which is available in the magnetic core material or iron core material. Okay, now we were seeing only about lossless transformer. Lossless transformer in the sense, already I told lossless transform in the sense we are not talking about core loss, we are not talking about copper loss, and we were talking about linear characteristics. Linear characteristics. When you are increasing the current, then the flux should be increasing. When you are decreasing the current, the flux intensity should be decreasing. So we were talking about this, where if you are increasing the H magnetic flux intensity, then the density will also increase like this. This is a linear fashion. Okay, now we have to talk about two more things. This is the EMF induced because this is the voltage across this particular thing. We consider that this is an inductor, right? So when the current entered this point, we told that the polarity is plus here and minus here. Because of that, we told that this is a voltage drop. Voltage drop. Okay, now this is nothing but EAB, that is, this is A terminal and this is B terminal. Now what we are going to do, we are going to write this as EBA. If you write this as EBA, if this is voltage drop, if this is voltage drop, then EBA is nothing but voltage rise. This is nothing but EMF induced. So now the same voltage which we have seen it as E is equal to N d phi by dt, this is the voltage drop and this is the voltage rise. So EBA is equal to minus EAB, that is nothing but minus E, that is nothing but minus N into d phi by dt. So what is this negative sign? This negative sign is giving the EMF induced here. So what is this induced EMF? That we are going to see. This negative sign is given by the Lenz law. Lenz law. Okay. So now let us see more about this induced EMF, that is EAB. So now you are having the transformer. Then in that you are having a primary winding. And in that primary winding, you are having some current. So now this is terminal A and this is terminal B. So now there is some current which is flowing through this path. If there is some current, then we told that by Fleming's right hand rule, the flux will be going in the upward direction. Yesterday we discussed about this. The flux will be moving out of this upward direction and it will be entering in this downward side part. So this is called as north pole and this will be considered as a south pole, right? Now this flux is inducing some EMF across these turns, that is the number of turns. We are calling that as EBA, that is going to be the induced EMF. Okay, now you know that the if EMF is induced because of this flux, because rate of change of flux is there which is linking the primary coil, right? So now you are having a source. Because of that source there was some current, because of that current there is some flux. So if the current changes, the flux also changes like this. So now what you are having, you are having a rate of change of flux. You are having a conductor, you are having a conductor. In that conductor there is some rate of change of flux which is linking this conductor. If rate of change of flux is linking this conductor, then you know that EMF will be induced. So the same thing, if it happens across this winding, then you can call that EMF as EBA, that is the induced EMF. Before, from the simple circuit perspective, we told that this is the primary winding, let's say, we told that the current is entering this path, then because of this current, there is going to be an EMF, or that there is going to be a voltage, so that you called it as EAB. This is A terminal and this is B terminal. So if you write KVL equation for this circuit, if this is V, then V minus V plus EAB is equal to 0. So that time, this is the voltage rise and this is the voltage drop. So now that time you will be getting E is equal to EAB. This is EAB is voltage drop. Now what we are writing, we are representing it as EBA. So when EAB was considered as voltage drop, now EBA should be a voltage rise. Now the same point we are telling here, the rate of change of flux is there. Because of that, there is some EMF induced across the number of turns. So let me draw it, the number of, okay, let me draw it. So now there is some flux. That flux is going to induce some EMF. So this EMF is induced, that induced EMF will be in such a way that that will oppose the cause. Okay, so means that there is a flux which is moving in this upward direction. Because of that flux, there is some EMF induced. If that EMF induced, it will be in such a way that if it supplies some current, that current will be opposing the cause for it. That is given by the Lenz's law. Okay, so this is the flux which is linking that coil. That flux is inducing some EMF. Then you call this as induced EMF E1. Okay, this is an induced EMF. Now, if this is an induced EMF, then if you consider like a source, okay, if you consider like a source, then what happens if this EMF is able to supply some current, that current will be in the opposite direction. Only if it supplies current in the opposite direction, it will oppose the cause. What is the cause for that induced EMF? The cause for that induced EMF is this flux. The cause for that induced EMF is this flux. This flux is inducing some EMF in this polarity, which is like this. Now, if I allow this EMF to supply some current, then that will supply current which is opposite to the actual current flow. Only if it supplies the current in that opposite direction, then only it will oppose the actual flux which is responsible for inducing this EMF. Okay, the Lenz's law says that always the response will oppose the cause. Always the response will oppose the cause. What is the response here? The response is the EMF induced. That EMF induced, if it supplies some current, then that current will oppose the actual current. In another way, you can say that if this induced EMF is allowing some current, because of that, if there is some flux, then that flux will be opposing the cause for it. The cause for this actual EMF is the flux which is supplied by the current, by the source. There was a current which is flowing in this direction. There was a current which is flowing in this direction. Because of that current, there was some flux induced. That flux is developed this induced EMF. If that developed EMF is capable to supply some current, that current will be in such a way that that will oppose the cause. So the current which will be supplied by this induced EMF will be opposite in nature to the actual current. Then only it will be opposing the cause. So the induced EMF will be having the same polarity. If you are considering EAB, that is the voltage drop, and if you are considering this EBA, that will be a voltage rise. This we have discussed when we are seeing about the first unit. Okay, so that concept will be applicable here. So yesterday we saw about the phasor diagram. So we saw that V1, V is there, then current is there. The current will be lagging the voltage, that is the source voltage, by 90 degree, because we considered this complete part as a pure inductor. Now that time, this E, V and EAB. What is EAB? EAB is the voltage drop across the terminal that will be in phase. Now I'm talking about the induced EMF. Induced EMF, that is a voltage rise. So voltage rise will be opposite to EAB, right? Voltage rise will be opposite to EAB. So in my phasor diagram, my EBA will be in this fashion. This will be equal to the E1. The E1 is nothing but the induced EMF. This induced EMF is because of the flux which is established because of the current which is flowing through the circuit. Okay, is this clear? What I'm doing, I'm having a circuit like this. In this circuit, this is V and this is EAB. This is the terminal plus, this is the terminal minus, this is the polarity plus and this is the polarity minus. The current is flowing through this. This is terminal A and this is terminal B. So now if I write KVL equation for this, I will be getting minus V plus EAB is equal to 0. So this is voltage rise and this is voltage drop. Now if I write this equation, I will be getting V is equal to EAB. So now if I draw the phasor diagram, this V will be here and EAB will be here. Both are in phase with each other. Okay. Now the current will be lagging the voltage by 90 degree. Now instead of writing it as EAB, this is a voltage drop. If I represent it as a voltage rise, then my EAB will be equal to minus EBA. I hope that you accept this because we have discussed this in the first unit. So EAB will be equal to minus EBA. So in that case, I can write V EAB. E, my current is here. Then the induced EMF, that is EBA, or the EMF induced across the primary terminal. So this negative sign indicates that there is a 180 degree phase shift. So this 180 degree is phase shifted from this actual thing. So here we are writing it as induced EMF. Here we are writing it as voltage drop. Here we are writing it as voltage rise. Okay. Why we have written like this? If we apply Lenz's law, it will oppose the cause. The cause for this EMF induced is the current which is flowing this. That current is going to induce some establish some flux. That flux is going to induce some EMF, that is EBA. Okay. Is it clear? Do you understand this? So if you see this, your V will be here, that is the source voltage or the voltage drop. Then your current will be here and your induced EMF is here. So this induced EMF will be lagging the current by 90 degree, and this source voltage is leading the current by 90 degree. Your flux is also in this direction. This is for lossless transformer. Is this clear? Do you have did you understand this? Okay, if you have any doubt, you can ask this, else we can proceed further. Okay, so yesterday itself we have seen the voltage will be leading the current. This is the source voltage that will be leading the current by 90 degree. Then flux and current will be in phase with in phase to each other. Then that both will be lagging the voltage by 90 degree. Okay, this is for a pure transformer without any losses. Okay, so here this phasor diagram we have drawn based on the circuit viewpoint. As I told, we had considered that this E1 as a voltage drop. So here it is mentioned as E1. So the voltage drop is given by EAB. Okay, so this is for circuit viewpoint. It depends on the current flows as well as in the circuit parameter L. One current is flowing, that is flowing in that inductor. So inductor, what they are telling about inductor is this part they are telling it as an inductor. Okay, so that's what they are saying. Then the second approach, till now whatever we had discussed, it's of circuit viewpoint. Now I discussed about one thing which is based on the flux, that is based on the Faraday's law of induction. Okay, so one is based on pure circuit viewpoint. That pure circuit viewpoint is this, and if you are telling in terms of magnetic Faraday's law of induction or magnetic field, then I told about one thing, that is this induced EMF. So when you are talking in terms of magnetic field, then you can consider that EMF induced will be like this. If you are talking in terms of simple circuit viewpoint, you can tell that we are having voltage drop. So here we are having voltage drop. This is based on circuit viewpoint. Then induced EMF we are telling that is based on the magnetic field, that is mainly because of the Faraday's law of induction. That is the only difference. The thing is we are just seeing in different viewpoint. That's all, nothing else. The operation is same. We are just seeing it in the different view. Okay, so here as you know, Faraday's law states that the EMF induced in the coil is proportional to the number of turns linking the flux. So n into d phi by dt, that is what they are saying here. So when we talked about simple circuit viewpoint, we can write it as EAB, that is a voltage drop, that is given by E1, that is given by n into d phi by dt. So in circuit viewpoint, we directly write it as V is equal to I into XL. So when it is given in the field point of view, we have to represent the flux. So in order to represent the flux, we have included d phi by dt. So this is a voltage drop. In order to represent it as a voltage rise, we have to take the negative of this. This negative, it will be given by minus n into d phi by dt. This negative side is given by the Lenz's law. It means that the response, that is this induced EMF, will oppose the cause. The cause for this is the current and the flux established by that current, which is provided by the source. Okay, so now we will be writing in terms of the flux. So flux can be writing it you can write the flux, total flux, as the flux is going to change sinusoidally, then that can be represented as maximum flux into sine omega t, because we have seen that if the current is sinusoidal, obviously the flux also will be sinusoidal. This phi m will give the maximum value of the magnetic flux, and this sine omega t gives the sinusoidal variation of the flux. So if you substitute this phi in this equation, then you just differentiate this equation. So the phi is given by phi m sine omega t. You differentiate this. So this is differentiated with respect to t. So when you are differentiating this with respect to t, we can write sine omega t differentiation as omega cos omega t. That is what it is written here, omega cos omega t. So remaining terms is appeared as it is. Now EBA is equal to minus E1, that is equal to E1 sine omega t minus pi by 2. This cos omega t is written in terms of sine omega t. So when you are writing in terms of sine omega t, we will be getting this equation. So this we have already seen in the yesterday's class. Then this omega n1 phi m, these three terms together can be considered as E1. That E1 is the maximum value that can be obtained for this induced EMF. Okay, now this E1 is the maximum EMF that is varying in the sinusoidal fashion, and that E1 max can be given by N1 phi m and omega. So this complete term can be written as root 2 into E1, because this is the peak value. So if you want to write it in terms of RMS, it can be written as root 2 into RMS value. RMS value is the E1 that is given here. E1 is the RMS value of the induced EMF. So now this E1 lags the flux by 90 degree. As per this two equation, you can see that flux is phi m sine omega t, and induced EMF, that is EBA, is equal to minus E1, that is EM1 max sine E1 max sine omega t minus pi by 2. So if you compare equation 10 and this equation, equation 11, then you can see clearly that this induced EMF is lagging the flux by 90 degree. Okay, this induced EMF is the voltage across the transformer primary winding that is induced because of this flux. So that is represented in the phasor. So this flux is here, and this induced EMF is lagging the voltage by 90 degree, that is shown here. Okay, now if you draw the phasor diagram, this is for the field point of view. In the circuit point of view, we have already drawn this based on this that we have seen yesterday. So this is based on the circuit viewpoint. So EAB is the voltage drop. With respect to that, the current and the flux are lagging this voltage drop by 90 degree. Whereas in the induced EMF, you can see here that this current is leading the induced EMF by 90 degree. Or you can also say that the induced EMF is lagging the current by 90 degree. Also, it is lagging the flux by 90 degree. Okay, so this is for different viewpoints. Now let us see about practical transformer, where in the previous case we have neglected the losses. Here we have to include the losses. Okay, so very simple loss which we can see in the very first thing is the core loss, copper loss, and there is one more loss, that is core loss. Okay, now let us say that we are having a transformer. In this transformer, I hope you would be knowing about hysteresis loop. In hysteresis loop, what is happening is, if you are increasing the flux intensity, then initially the magnetic field will be increasing. Then after some time it will get saturated. So you are increasing it, and it is if you are increasing the flux intensity, then the flux density will also increase. So now you have increased to certain position. Then after that, what you are doing, you are, just a minute. So you are increasing the flux intensity. This is B. The B is also increasing. Whereas when you are trying to bringing back to zero, when you are trying to bringing back the intensity to zero, that time what happens? The immediately the flux density will not become zero. It will be having some value. Okay, we are starting from zero. When you are increasing the flux intensity, then the density will also increase gradually. Whereas when you are trying to bring it back to zero of the intensity will become zero, whereas the density will not become zero. The reason for this we will see in the next class, but we will proceed further with this. So when H is increasing, then B is also increasing. When you are trying to reduce the H, then B will not comes to zero immediately. It will be having certain value even if you bring back the intensity to zero. So if you are further extending the curve, then your intensity, if you take it to the negative value, then only your flux density will become zero. So if you are proceeding it further, so the same thing will be happening in the reverse way. You are increasing the intensity to the negative some value, then that time you are getting the maximum flux density. So now if you are trying to increase the intensity again, that is the flux intensity again the flux density will not become zero. Then it will become zero only after you are increasing this H. Okay, so again, if you are increasing it, it will be going like this. So it will be keep on having a curve that will be like this. If you consider it as a loop, this loop is considered as a hysteresis loop. In hysteresis loop, what is happening is, when you are increasing the intensity, the flux density will also increase. But when you are trying to bring the intensity to lesser value, then the density will not reduce proportionately with the H. So because of that, there is some density is there even after you remove the intensity of the magnetic field. So this particular part is called as retentivity property of this material. Retentivity property of the material. So in some experiment which you could have performed in your lab, shunt generator, those who have performed magnetization characteristics of shunt generator, magnetization characteristics of shunt generator, you would have seen that when the field current is zero, the induced EMF is not zero. Okay, some of you, those who have performed those experiments, you would have seen when the field current is zero, the induced EMF is not zero, because the material which is used in the machine will be having the retentivity property. So that time, even though the field current is zero, there is some magnetic flux, which is still, or there is a magnetic field which is still exists in the material. Because of that, even if the field current is zero, the magnetic field is not zero. Because of that, there is some EMF induced even though the field current is zero. Okay, so this is considered as the hysteresis loss. This is considered as a hysteresis loss. Then there is one more loss that is called as eddy current loss. Eddy current loss I discussed yesterday. Because of the rate of change of flux, there is some flux which is established within the core because of the induced EMF in the core. So that current will changes according to the frequency of the supply. So that current will be flowing within the material. So that current will make some heat dissipation. That heat dissipation is also a loss. Okay, so there are two losses in the system. One is copper loss and core loss. Copper loss is given by the current which is flowing in the winding, whereas the core loss is depending on two things. One is hysteresis loss and the second one is the eddy current loss. Okay, so now the third one is the copper loss. Copper loss, any conductor will be having its own resistance. So if there is some current flowing through this path, obviously there is going to be some resistance which is available in this path. So that resistance will be having some power loss that is given by I square R, right? So these three losses we are going to incorporate one by one. How we are going to incorporate that we will be seeing. Okay, so mainly the loss will be represented in terms of heat dissipation. So in order to represent the heat dissipation, we are going to represent as power dissipation in terms of resistor. Okay, in terms of resistor. So now the point is, we'll be seeing much in detail, but as of now, we'll consider that there is some current which is going to flow through this path, and there is some EMF induced across this winding. Now we are having the copper loss, which is represented by some resistor, that is R1. R1 is just the resistor which is representing the conductor losses. Okay, because if there is some current, there is some power loss which is going to happen in the conductor. So that is given by the conductor loss, that is mentioned by the resistance R1. Okay, so now other than this, we are going to have copper loss. That copper loss, this is copper loss, and second one is the core loss. That core loss we need to represent. Okay, so how we are going to represent? So before we are going to represent that, here we will consider two amount of current is there. Two current quantities are there. One current which is going to establish the flux. Okay, that is given by I5, and there is one current which is going to responsible for the losses. Okay, we just consider that there is some loss. For that loss we are representing it as IC. Okay, so now this current is going to flow through the resistor. Okay, so this current is going to flow through the resistor. So this current and this voltage will be in phase with each other, right? Because if there is some current, then that current is flowing through the resistor, then that current and the voltage across that will be in phase with each other. Okay, so as of now, we just consider that we are having the EMF, that is E1, then you are having the actual current, that is I5. This current is responsible for supplying the magnetic field, or establish this current is responsible for establishing the flux or the magnetic field. There is one more current that is responsible for the losses in the current. So that current will be in phase with the voltage, because this is going to be a loss. Mainly it is going to be heat dissipation. Heat dissipation will be representing in the resistor. So here the EMF, the voltage and the current will be in phase with each other. Okay, so this is the current which is going to flow, that is in phase with the voltage, and there is another current which is establishing the flux, that is 90-degree lagging to the EMF. Now the overall current we are going to represent it as magnetization current. This is the overall current, that is a magnetization current, that is given by the vector sum of this current and this current. Okay, so Im is the overall current. That current is divided into two parts. This current is considered as magnetization current, that is having two components, that is given by one is IC and another one is I5. So this I5 is responsible for establishing the flux and this IC is responsible for representing the losses. Okay, so that is what I wanted to tell about this. So let us proceed further. Now this is for the current which is flowing through this, that is going to be having flowing through the resistive part. That resistive part will be in phase with the voltage, that will be in phase with the voltage that is given here. Okay, now we'll go back. That is the resistance R1. In that resistance R1 there is some voltage drop. Okay, in the previous case, in the practical transformer, we considered one condition that if you are having a practical transformer, when it was represented like this, then whatever the EMF, this is V and E1. So here V is equal to E1. Now when you are adding a resistor here, then V is not equal to E1 anymore, because V is equal to the, let's say this is a voltage drop across this resistor, that can be given by VR plus E1. Okay, this will be the overall voltage because we have added a resistor in series that is representing the copper loss. That copper loss is given by I square R. Because of this resistor, there is going to be a voltage drop across this. So the overall voltage V can be given by VR plus E1. Okay, so now also we are representing it as voltage drop. So V is equal to VR plus V1 E1. So this V is the source voltage, VR is the drop across the resistor, and E1 is the induced EMF, voltage drop across this terminals. Now let us draw the phasor diagram again. So this is E1. Now this is I5. Then again we saw some current, that is IC. Right? This is for the previous case that we have seen. So then we have seen about magnetization current. That magnetization current was flowing through this path IM. Right? Now okay, you can see this current IC and IM, and this is I5. These three current we have talked about already. Okay, now V1 is the voltage, that is sum of the voltage of E1 and IM R1. What is IM R1? That is the current flowing through the resistor in that particular path. Okay, so the point is, you are now this V is equal to VR plus E1. Now if you draw this in phasor diagram, your E1 is here, E1 is here, then your IC is here. This is going to represent the core loss component, and then you are going to have one current, that is I5. Then you are going to have the resultant current, that is IM. IM is the magnetization current, you can call IM. Now we wanted to represent this V. V is nothing but VR plus E1. So this VR can be written as IM into R. R is the resistance of this particular winding, that is given by R, right? So now this IM is the current flowing through this resistor. So when you want to represent this VR, then you can write it like this, because this IM will be in phase with this voltage. IM will be in phase with the voltage, that is nothing but VR. Okay, so when both are in phase, you can take it in the parallel component like this. So this is VR. Then the summation of this E1 plus VR will be giving the voltage, that is nothing but V. Okay, this is very simple. There is no record to, don't get confused. So we are having the circuit like this. So in this circuit, we are having E1 here. So there is some EMF which is available here, that is considered as the voltage drop. Then there is some core loss component that is represented by IC. Then there is a voltage drop in the winding, that is a copper loss, that is given by I square R, that is based on the current flowing through this. This resistance is R. Then we are telling that some current is flowing through this path, that is Im. Okay, so this is Im square R. Now this is the voltage V. So V is equal to the voltage across the resistor plus the voltage drop across this inductor. You can consider like a RL circuit. Okay, this is R and this is L. So now we have to draw the phasor diagram for this circuit. So for drawing the phasor diagram for this circuit, we know already E1 and we know one current, that is I5. So this is the starting point of our phasor diagram. Okay, this current was there which was establishing the flux. Now we are separating this current along with the current which is responsible for loss, the current which is responsible for the loss, which will be in phase with the voltage. So that will be given by IC. Okay, so this is going to represent the copper loss current, sorry, core loss current, which is going to happen within the core. So the summation of these two currents, we are going to represent it as Im. This is the current which is going to come out of the source. Now we have written E1. We wanted to represent V in phasor diagram. What is V? V is nothing but VR plus E1. So now we have to write this VR. What is VR? VR is the voltage drop across the resistor, that is given by Im into R. This is the resistance value. So this is the voltage value. This voltage value will be in phase with the current Im. So if it is in phase, you can take the Im in the same direction in order to represent that this is Im1R, this is nothing but VR. So here VR is in phase with Im because it is a resistor. So VR will be in phase with the Im. So we have taken parallel to this Im component. Now we wanted to write VR. V is nothing but the vector addition of VR plus E1. All are vectors. It is not scalar. All are vectors. Okay. So now you just add it, both the components. We will be getting V. So we have drawn the very basic phasor diagram for a transformer which is having only the primary winding, which is like this. Okay. Still further components need to be added, that we will be seeing one by one now. Okay. So now this is the core loss component, and this IMR1 is going to be the voltage drop, and this IM is going to create a copper loss also. So that you can see here that input power can be written as V1 IM cos theta, that is having the core loss component, also the copper loss component. Okay, so if you put a wattmeter here, that will be measuring some power, that will be accounting for both power loss, that is the core loss, and copper loss. Okay, so we will be seeing further about this. Till now we were discussing only about the single winding transformer. We have seen only about the primary winding. Now we will be including the secondary winding also. Okay, so now we have already seen E1 as voltage drop. So if there is some E1 which is if you are representing it as induced EMF instead of a voltage drop, then the voltage magnitude can be written as root 2 into E1, which is equal to N1 phi m into omega. This is the induced EMF in RMS. So this root 2, if you take it to the right hand side, then we will be getting this expression. So this omega is nothing but 2 pi f. So f is nothing but the frequency of the signal. Okay, now we have written one expression. This expression will give the EMF induced because of the current which is flowing through this path. So now we are not representing in terms of current, we are going to represent it in terms of flux. So this equation, if you further reduce it, we will be getting this expression. E1 is equal to 4.44 flux phi m and N1. Okay, now this is the induced EMF. Similarly, the induced EMF on the secondary turn can be given by 4.44 F into phi m into N2. You can see one thing, that the flux which is available here is linking both the primary and secondary. Since the same flux is linking both the primary and secondary, the induced EMF E1 and the induced EMF E2 both will be in phase with each other. Okay, so since both the flux are linking the primary and secondary, we can say that the induced EMF E1 that is on the primary winding and the induced EMF E2 that is on the secondary winding both will be in phase with each other, even though the magnitude may change because of the losses, but both will be in phase with each other. So now if you take the ratio of this, that is 17 divided by 18, then you will be getting E1 divided by E2 is equal to N1 divided by N2. I have just divided 17 by 18. So if I do like that, I will be getting E1 divided by E2, which is equal to N1 divided by N2. So this is called as a ratio of transformation, you can call, or you can call that turns ratio. You can call this A as the turns ratio. So one thing you should be noting it down, even though if you are having different number of turns on the primary and secondary, the voltage may differ or the current may differ, whereas the power will always be same between the primary and secondary except the losses. If you neglect the losses, both the primary power and secondary power will be equal. Okay, so to be practical, if you write secondary power is equal to the primary power plus losses in the transformer. So if you neglect the losses, the primary power will be equal to the secondary power. So if you equate primary power is equal to secondary power, you can see here that E1 I1 is equal to E2 I2. If you rewrite this equation, you will be getting E1 by E2 is equal to I1 by I2 by I1. That is equal to A. In another way, you can write I1 by I2 as 1 by A. Already we have written E1 by E2 as A. Then you will be getting I2 by I1 as A in terms of current. So this is considered as the turns ratio. And if you want to write it in the reverse way as I1 by I2, then we have to write it as 1 by A. Okay, so as I told before, E1 and E2 are in phase because they are induced by the same flux. Okay, now we will be seeing transformer phasor diagram at no load condition. So now we will be seeing more about practical transformer rather than simple transformer without losses. Already we have included simple core losses and copper losses by using the resistor, and there is one element that we will be discussing about that later. Okay, now you can see that there is a voltage source, that is V1, then that is supplying some current, that is Im, then there is a resistor which is indicating the drop in the line or the cable. Now because of that current, it is like it is passing through the number of turns. Because of those number of turns, you are going to get a resultant flux. Now that flux is going, some flux is going to link both the primary and secondary, and some flux is linking only some part of the turns in the primary only. Okay, you can see here that which is represented in red color mark. So here the red color one is linking only the primary, and that is not linking the secondary. Only some flux is linking the primary as well as the secondary of the transformer. Now you can see that flux which is linking only the primary, that also not linking all the turns which is existing here. Some flux is linking all the turns and some flux is linking only some turns. Okay, so now the flux which is linking both the primary and secondary is called as mutual flux, whereas the flux which is linking only one winding, that is the primary winding, and not linking the secondary winding, that is called as leakage flux. So I have indicated indicated in a red color. You can see here that this flux which is linking only the primary winding, this is not linking the secondary winding. So out of the total flux can be written as mutual flux plus the leakage flux. So here that leakage flux links only the primary coil, that is not linking the secondary coil. So here this flux is seeing the reluctance as higher magnitude, and this flux will not see more hysteresis path, because this flux, most of the flux is existing on air. Since the flux exists on air, you cannot have hysteresis loop. because hysteresis loop exists only for a iron material or some magnetic material, whereas air is not a magnetic material. So when you are increasing the current, then the flux will increase immediately. When you are decreasing the current, the flux will decrease immediately. Even though it is linking only some part of the iron core, the flux and the current will be in phase with each other. Okay, so that we will be discussing. So here the current which is flowing here, because of that there is some flux intensity. That flux intensity and the magnetic field, because of this leakage flux, both will not face any hysteresis loop, because here most of the flux is linking the air rather than the iron core or magnetic material. Because of that there will not be any hysteresis for the leakage flux. So in order to mention that the primary leakage flux is in phase with the primary winding current. Okay, the primary leakage flux is in phase with the primary winding current. Okay, so the EMF induced because of this phi L1, that is the leakage flux on the primary, that can be given by EL1, that you can see here, that you can given by EL1. So this voltage or EMF induced is lagging the it's leading the flux by 90 degree. Okay, so this is like a source voltage that will be leading the flux by 90 degree. Okay, so this EMF is representing the leakage flux. If there is no leakage flux, then there would have been more EMF induced in the circuit. Now because of the leakage flux, let's EMF is induced in the circuit. The EMF which is induced on this path, we will be considering only happened because of the mutual flux. I repeat, we are having certain equation, that is phi m. This phi m is a flux which is linking both the primary and secondary coil. So whenever you are representing the induced EMF, we always consider that the induced EMF is because of the mutual flux only. Okay, so this is a two winding transformer. After that, you can see very clearly that till now we did not talk about the leakage flux, but there is some leakage flux. That leakage flux also is capable of inducing some EMF, but whenever we are writing induced EMF equation, that we are going to represent only the mutual flux. Okay, so the EMF which is induced because of that primary leakage flux, that we are writing it as EL1, so that we have to represent it in our circuit. Okay, now as I told before, this flux is going to be in phase with the current, and there is going to be an EMF induced because of the leakage flux. Okay, so only one thing which I wanted to tell. So here you are having one thing, that is induced EMF because of the leakage flux. But whenever you are writing the induced EMF equation, there when you are writing the induced EMF equation, you got N1 phi omega. This phi is only the mutual flux. This phi is not including the leakage flux. Okay, whenever you are writing the induced EMF equation, we are going to represent only the mutual flux. We are not going to represent the leakage flux. But we want to represent this EMF induced by the leakage flux by somehow. So in order to have that, we are going to redraw this circuit by representing as an inductor. Okay, so now you can draw the circuit like this. Now we can remove the leakage flux, because the leakage flux has been represented as an inductor, that is given by the series reactance, that you can represent like this, inductive reactance. Okay, so this will account for the leakage flux which is existed across this, that may be inducing some EMF. So now the EMF induced across this terminal is because only of the mutual flux. There is some flux which is leakage flux, that is linking only the primary and that is not linking the secondary. That is going to be represented in the series, because that is going to induce some EMF. So this is nothing but EL1. This is a fictitious element, it is not available as it is. But in order to represent the leakage flux which was existing here, in order to represent this leakage flux, what we are doing, we are removing this leakage flux and we are representing this in this fashion. Why we are drawing it in series? Because the current flowing through this will be in phase with the flux which is established by this field. So whenever the current is increasing, then the magnetic field, the flux will also increase. Why it is happening like this? Because I told that in the leakage flux, since it is linking only some part of the magnetic core, the hysteresis path will not be seen by this leakage flux. Because of that, the whenever you are increasing the intensity, then the flux density will increase. If you are reducing the flux density, then when you are reducing the flux intensity, then the density will also decrease. So this relation will be linear. So in order to represent the linear relation, this current should be in series with this inductance, then only you will be getting the series relation. Other than that, linear relation, yeah, other than that, you are representing that in series because it is going to represent the voltage drop because of the leakage flux. Okay, so we will end this class now. If you have any doubt, you can ask, else you can end this meeting. If you are having any doubt, you can ask, else we can end this meeting. Thank you for joining.
Thank you, sir.
Thank you, sir.